Good morning, good afternoon, good evening, wherever you are on this beautiful planet. My name is Frank Marchis. I'm a senior researcher at the SETI Institute and chief scientific officer at Unistellar. So today we are going to talk about the moon and specifically one tiny part of the moon. And for that, we invited Matt Ziegler. Hey, Matt, how are you?
Hi, nice to see you.
Nice to meet you. You are a senior scientist at the Planetary Science Institute, and you're the first author of a paper that was published this week, I think, in Nature called Remote Detection of a Lunar Granitic Batholith Compton-Belkovich. Okay, and that's the goal of this
Just
SETI Live
let's
is to
translate what that means.
exactly each of those terms and so people understand what the title, at least the title of the article, is about. Before digging into this research, I just would like to mention to our viewers, you can tell us where you are watching us from, and we are also going to take some questions from you live. So take the time to listen and to start posting questions in a few minutes. So, um, Matt, let me go through my outline. What is this discovery you made with the Chang'e 1 and Chang'e 2 instrument? And what exactly are those instruments?
Okay, well, to break down the title, the first thing is Compton-Belkovich. All right, so basically, there's this weird kind of nondescript area on the moon that's like halfway between Compton crater and Belkovich crater, and there was nothing too odd about it until in the 90s, the Lunar Prospector orbiter flew over this and saw a high concentration in thorium with an instrument called a gamma ray spectrometer. So it's been kind of this weird thorium anomaly on the moon
Mhm.
that no one ever really figured out why it was there or what was so special about it. Over the last 20 years, people have looked and seen evidence that it looks kind of like it could have been a volcano at one point. And so what we've added to this story now was that with the Chang'e 1 and 2 orbiters, they both flew an instrument called a microwave spectrometer around the moon for the first time. Or a microwave radiometer or spectrometer basically is like an infrared camera, but now imagine with longer wavelengths than infrared. So microwave is the next longest wavelength from infrared. Instead of seeing the temperature at the surface, now we're going to see a little bit of temperature in the subsurface.
Mm-hmm.
And so what we've been able to do is now piece together the Chang'e data to map out places where temperatures are hotter than expected under the surface of the moon. And that's places where you have a higher geothermal gradient, where temperatures are getting hotter with depth. And what we found was there was just a lot of extra heat also coming out of this Compton-Belkovich feature. So not only was it a weird concentration of this thorium at the surface, but it also was glowing hot in this microwave instrument.
Okay, so when you say glowing hot, are we talking about thousands of Kelvin of degrees Celsius like we have on volcano of Earth? Or are
Yeah.
we talking about 100 Kelvin? Or what's the
Oh,
glow?
yeah, yeah. So it was 10 Kelvin brighter than we expected it to be in the microwave instrument. A microwave instrument is inherently pretty low resolution. It has an antenna, maybe as big as a dinner plate. Its pixel is around 25 kilometers or so on the surface. And so that 10 Kelvin could be a higher signal over a smaller area. We think in reality it would be then this is in brightness temperature, which is the increase in temperature at that specific frequency, right? Then we see maybe 35 Kelvin brightness temperature increase there. But that means it's hot. And what that equates to and what we then did a model of is how much extra geothermal heat do you need? And the background moon, just from the radioactive content of the crust of the moon and everything, should give out maybe 5 to 10 milliwatts per meter squared is the unit we measure heat flow in. And this one we are estimating is something like 180 right? So this is something that's roughly 20 times hotter than the average moon, the
Okay.
background moon, and 20 times hotter than what the Apollo astronauts measured with heat flow probe instruments in the 1970s. So it's glowing.
Now, excited. It's a nature paper after all, so it's exciting. Okay, before we go into more details about that, we have people joining us from Canada, from Peru, Florida, from the moon, from Australia, from Caledonia, Illinois, Texas. Oh my God! Every time we have someone, from UK, I have to think twice before saying the name of the city. Oldham, Wiltshire. I'm sorry. In the UK, I cannot say the name of city. I'm sorry for that. Australia, of course, Santiago de Chile. Hola. New Orleans, more Florida. People from Florida. Thank you. We are talking with Matt today about an area of the moon in the Compton-Belkovich area specifically, which seems to be glowing and slightly hotter than the rest of the surface. So now, you have detected this using the Chang'E instrument you mentioned, two of them. You have an idea of the temperature of this area, the excess of heat, basically. So what? What is this coming? How this was formed? What's this coming from?
Yeah, and so now you need a way to create a bunch of heat in a specific area on the moon. And like I said, people kind of mapped this area of potentially being a volcano, but a volcano that erupted 3.5 billion years ago.
Mhm.
All right. So this is not like a glowing hot volcano because it's still active. And so where's that heat coming from? That heat has to be coming from the radioactive elements that are in the materials that that formed underneath the volcano. So when you melt some of the crust of the moon, that molten material, the first things that go into the melt are the elements, or a lot of things, but primarily elements silicon, and then you also get concentrations of radioactive elements like uranium and thorium that produce heat. And so every time you remelt some of the crust, you form a more concentrated mineral, right? And so we start off with basalt, and that's most of the volcanism on the moon. All the dark spots, the mare of the moon, are all basalt.
So what you see in Hawaii, for instance, or Reunion Island, the volcanoes there have this black lava,
Yeah,
very fragile element. Those are basalt.
yeah, and basalt has low silicon and low thorium and uranium, right? And so it's very flowy. It doesn't form a tall mountain. But then, Mount St. Helens or something like that forms a pointy volcano. That's because it has a lot of silicon in it, and it also has a lot of uranium and thorium. And those, when it erupts to the surface, we call it rhyolite. When it's under the surface, we call it granite. So like your granite countertop. So your granite countertop does have more uranium and thorium than a normal rock if you had a basalt countertop, I guess, if anyone does that. But yeah, and so basically from the heat we saw coming out of the ground, the only explanation for it that we could find was that there was a really large body of granite below the surface of the moon. And that's weird because on Earth, almost all granites form because of water and plate tectonics.
Yeah.
Which isn't on the moon, right? The moon doesn't have water, plate tectonics. How did this weird thing form? And so it's kind of one of these fun problems in planetary science where you have to take all the models that have always worked for Earth of how you form a material, but now you have to do it under this situation where things are different. You need either this part of the moon to have been oddly wet, this part of the moon to have been extremely hot. Maybe we're seeing evidence that there was a mantle plume, kind of like you have under Hawaii or Yellowstone, have mantle plumes under them on Earth, right? So we might be seeing the Yellowstone of the moon essentially in this location.
Yeah, that's a very good analogy. So you may have seen some weird area of the moon where the volcanic activity was more intense. And what we have now is the remain of this volcanic activity, and this maybe a granite magma chamber or something like that. in the surface? Are we talking about like 100 kilometer deep, 20? What's the...
So the crust in this area from the Grail gravity mission is estimated to be around 40 or 50 kilometers thick. And what was kind of neat from the Chang'e data was it was at multiple frequencies, and each frequency would see a different size.
Huh?
And so you could actually reconstruct how wide the heat source had to be. And then as you know, so we could create a model of this body below the surface producing heat. And then as you move it down too much, then that heat will be able to spread out further. So we could actually figure out that we had to have a body that was about 50 kilometers in diameter, that was about halfway through the crust, 25 kilometers below the surface of the moon.
Right.
Yeah, and then there's evidence on the surface and evidence from the heat flow as well, that we then have a second chamber above that that actually reached to the surface and caused the eruption. So yeah, so it's kind of fun that just from this data we were able to piece together this whole system that's very much like volcanic systems we're used to on Earth, and we're not used to seeing systems like that on the moon.
All right, let's go back to this later on.
Sure.
We have people joining us from different parts of the world. No, I'm not in Ibiza. This is a recurrent joke. Don't worry. Yes, Granite. Manchester, UK. Welcome. That's a city I can say. Everybody's repeating Granite, so I think they're all coming from Granite right now. No, really. Mountain View, California, Nazaim, some colleagues of us probably. And we have more people from Mountain View, in fact, and Las Vegas as well, and so on. So thank you. You are talking, you are watching a SETI Live with Matt Ziegler, and we are talking about an anomaly on the moon, some remains of a volcanic activity, probably, I would say. So how important it is the fact that we have discovered a granite magma chamber, maybe, in underneath the surface of the moon?
Yeah, I mean, so it's basically showing us that, all the volcanism that we have seen really on the moon, or maybe on Mars, there are a few of this more evolved volcanism where you go through multi-stage volcanism. Basalt, like I was talking about, the flood basalts like we see on the moon, or that cover most of Mars, or probably cover Venus. That's all one and done volcanism. Something comes, material comes up from the mantle, comes to the surface, blop, it's done. This multi-stage volcanism, like we're seeing, has to require a long source of heat over a long time. It's something that's, more sustained. On Earth, like I was saying, it usually involves wet crust from the plates on the ocean floor getting pulled down underneath. Wet crust melts at a lower temperature than dry crust, and so that then can remelt and then come back up to the surface, or aid in the melting of other materials in the crust and come back up to the surface. And so, yeah, forming all these without that whole process is kind of neat. And there are a few other locations like this on the moon, but they're all in the most active regions of the moon and such. So it's exciting from that perspective, as far as that we're able to now see this weird evolved volcanism on another planet other than Earth.
Yeah.
And then the other neat thing about it is no one's ever used this type of instrument on a planetary surface before. We have a similar instrument on the Juno mission that's going around Jupiter right now, and we're trying to do a similar thing, looking at temperatures below the surface on Ganymede and Europa. And coming up soon, we're going to fly by Io with that same instrument. But this instrument that went around the moon was really the first one to go around a solid body planet, and show that we can actually have this new window into what's going on underneath a planet's surface. And I'm really excited about that kind of thing. We've done a lot of imaging of the upper millimeter of all the planets. And this is a new tool to be able to look into what's going on in the subsurfaces.
Yeah, before we take questions from the audience, I have one question for you. So, you use an instrument made by the Chinese Space Agency.
Yeah.
I'm assuming Chang'e 1 and Chang'e 2
Yeah.
are operated by those by the Chinese Space Agency. Um, how is that possible? I mean, you live in the
Yeah.
US. How do you have access to this data? What was the mechanism for that?
I mean, and so this is like, kind of one of these things of science, getting over politics, which is always pretty exciting, and their planetary science has always been, a spearhead of this, like all through the Cold War. We were working with the Venera data from the Russian landers and such. And NASA has always been, we have a rule at NASA where like all data basically has to be public within 6 months
Yeah.
after we take it, right? And there's no international law that says that has to happen or anything, but the Chinese Space Agency has followed suit and also is making their data public for that kind of thing. And so these were data that have been public since roughly 2015 or so, and just we finally worked at them long enough that we figured out what they meant. And you had to had to like dig through some papers that might only be published in Chinese language to try to figure out like what how does the calibration work and such. But yeah, we were able to crack through the data and really get to what it means.
Yeah, so you have the data coming from the spacecraft that has been stored somewhere in the
Yeah.
file that is kind of readable, but you also have to learn how the instrument operate and how the instrument takes data, because probably the sequence of data is different, the calibration and so on.
Yeah, and with this type of instrument really hasn't been flown anywhere before. We use them for Earth atmospheric observations a lot, and that's essentially why this instrument went to the moon at all. Was the Chinese space program wanted to send something to the moon. They needed instruments that have been flight qualified. They had this very successful weather satellite instrument. They said, "Oh, let's send that and see what we measure." And this is one of the exciting things that came out of that.
And you speak Chinese yourself? You read Chinese to be
No. But my co-author and postdoc that did a lot of work on this is from China himself, so he was able to really help with that. So that's Zhengqing Feng. He was very instrumental for all the data analysis and work on this.
So you continue a tradition that was initiated by people like Carl Sagan, basically, of making planetary science a bridge between countries, even though politically speaking there is some issue. Scientists of China in China or in the US can work together specifically on projects, and I think that's something admirable that I personally like. And
Yeah.
a lot of people believe that we need to always continue communicating with people across this planet to learn about each other and to learn what's going on.
Yeah, and right now basically the rule is that we are not allowed to use NASA funds from the Wright amendment, which was back in the 2011 budget for NASA. We're not allowed to use NASA funds to directly collaborate with China, right? But we can still work with them within the rules, and I think I've gotten some feedback from Chinese scientists as well that they're excited that we've been able to get some neat results from their hard work too.
Yeah, it's a win-win for everybody, for you to publish a paper, for the Chinese Space Agency to have their data being published and to show the usefulness of these observations or this data set in general, and bring some new ideas of things that can be done in the future with future space mission, or even just reanalyzing some of the data that was missed.
Yeah, and that's what we have so much data right now that I think there's just a lot of, I really like these projects where, this was a 10 plus year old data set by the time we were really looking at it, and we can, get out this new information from old data.
Okay, we're going to take a few questions from the audience. So there's a very technical question from Tommy Gilbenson. Are you ready? I hope you have your scientific, you have your nature paper in front of you. So the normal moon heat flow is 5 to 10 milliwatt per square meter, and we're detecting 150. Is that exact? Is that the exact number, or use roughly this?
Oh, I mean, so it, like I said, some of it is spread by the, by our model of how the antenna is viewing, and if the antenna pattern is slightly different or whatnot. But we fit, our best fit was 184 milliwatts per meter squared as being the peak heat flux. But if it were 150, I wouldn't be surprised.
Okay.
So there's some error on all these things.
What mean the word batholith in the title of your article?
Sure. So when you have material under the ground that's coming up under a volcanic caldera, that blob of hot material that's come up, we call that a pluton. And essentially, once you get enough of these plutons over time stuck together, and they grow into a large, body, and sometimes it's very homogeneous, like we have the Sierra Nevada mountain range is also called the Sierra Nevada batholith, right? Because it's one big, pretty continuous compositionally body of uh, of different granite materials that have come up over time, and kind of glued together. And you can see, actually, over time, the composition's changed, and you do have this part of the batholith is a different composition and such. But yeah, so it's basically, batholith is just a really large magma body below the ground.
Okay.
That's solid, I guess.
Okay. Let me just go through the questions. I'm trying to keep them in order. Um, so, could we use this material, the thorium and so on, as for mining later on? Is there an industrial application of the discovery of this granite in the bottom
Yeah.
of underneath and the thorium on the surface?
Yeah, I mean, so yeah, you could make more than countertops out of these materials, I guess. But as far as, it's at this high a heat fluxes, it's comparable to what we use for geothermal power sources on Earth, where you would like start to say like, oh yeah, this is something would power something by. But then you have to think about most geothermal power on Earth is from, pushing water down a tube and getting it hot and having it come up. So now we need to bring a bunch of water with us to make that a reasonable source. But maybe this could be a geothermal power source for a future moon base. Of course, having uranium and thorium are evidence that you have a lot of other of the rare earth elements concentrated in this location. And so, yeah, I mean, as far as all the modern technology we build using rare earth elements in general, I think this would be one of the higher concentrations. And then, around volcanic systems, around caldera systems is where you get copper and gold deposits and such on Earth. But that usually involves interaction with fluid, with water around there. So I don't think we'd expect that to happen on the moon, but it could still be that that we get concentrations of elements where you had this higher heat source.
So where is the Compton-Belkovich area? Is it dark side, far side, latitude, longitude?
Yeah, so it's about 60 degrees north on the far side of the moon. So kind of, it's like 100 degrees around. So 90 degrees would be the terminator that we can see. So it's just behind what we could see. And what's weird about it being there is, like I said, there's lots of volcanism on the moon. Most of it is this flood basalts, right? And that's almost all on the near side. And Compton-Belkovich is this one weird, really odd. The most extreme volcanism on the moon is in a separate environment from the most of the rest of the volcanism on the moon. So why did it get there is a big picture. Is a big question.
Yeah, it's interesting that the body which is the closest to us is still so full of mystery. We still have no idea about why the active volcano, the Maria on the near side and the far side is so different. for
Yeah,
instance.
yeah. It's when we first saw an image of the far side of the moon,
That's
from
yeah.
early Russian orbiters. It was just like, huh, that's weird. It doesn't look at all like the near side. And we still haven't really figured out why there's this near side far side difference. Yeah, so it's
So before we wrap up, are you yourself involved in those new missions to the moon? Those new um,
oh
the
the
ones to be launched by NASA, but also the Indian one, etc. Are you involved in those?
Yeah. So there's a series now coming up over the next 5 years of these commercial landed instruments. They're called CLIPS, or Prism is the name for them. And I'm lucky enough to be involved in 4 of those landers with different instruments. 2 with infrared cameras that we're going to land, and then 2 with geothermal heat flow probes. So the same way we're trying to use this microwave instrument to measure the geothermal heat with depth, you can also just stick a thermometer in the ground. And so that's what this geothermal heat instrument's going to do. And so that's really exciting. And then led out of NASA Ames, where you are, is the Viper mission. And I'm part of that. We're doing modeling of where, again, I do all these models of temperature underground. And so from that, we can predict where it's cold enough that ice could be stable underground. And so I'm working on the Viper mission, mapping where we might drill with that instrument to bring up ice from the subsurface. So yeah, there's a lot of exciting stuff coming up on the moon. And the first NASA landings are supposed to be this fall and winter. So hopefully we can do as well as the Chinese and Indian space agencies, and we'll see what comes.
All right. Yeah, I just want to mention that we tried to stick a thermometer in the surface of Mars, and it did not go well. You
Yeah,
were
yeah. So
so
that, yeah. So I was working on this too. So it was,
back
it was,
bad
it
memory.
was, yeah. It basically was, Mars kind of threw us a curveball in that we had tested this instrument on all sorts of types of soil and in Mars-like environments, and the mole on the Mars drill kind of worked like a jackhammer, where it has a spring-loaded system that would hammer down. And jackhammer works on the principle of there's a guy holding the jackhammer, right? that is keeping it from just bouncing in place. And so we expected the Mars soil to collapse in a pit around our instrument and provide that force constraining the mole in place. But the soil ended up being a lot more cohesive. I think of it as like brown sugar versus regular sugar. And so the rigid walls didn't fall in around us. They didn't provide that constraining pressure we needed to actually push down. And so it was a really great instrument design, and it worked very well, and it would have worked tremendously well if we had gotten past that upper 10 centimeters or so. But the fact that we got stuck with this very cohesive soil so near the surface was really a problem that design couldn't really tackle. And this heat flow probe that we're sending to the moon, the Lister heat flow probe, uses a new design where it kind of blows air out of the tip of the probe as it pushes down into the ground. Viper has a drill as well that's using the old classic auger drill design. And so we'll see over the next few years if one of these other designs for getting into the subsurface of a planet is more reliable in general. But I still think the mole, is a great design in its own right, and it has a lot of potential to work eventually.
Okay, well, I wish you good luck with all these new missions you're gonna be involved. I'm sure we're gonna hear about you pretty soon. I would say pretty soon, in the next year or two, when we have those missions on the moon.
Okay, well, thank you. Thanks for having me.
Thank you very much, Matt, for explaining to us how we measure an excess in temperature by less than 10 Kelvin on the surface of a moon, and how excited this could be for geophysicists and people, especially who are interested in volcanic activity on the moon. I mean, that's a major discovery, and that's why it was published in Nature. Even though the title is not fancy, I must admit that I really love reading the press releases and part of the paper to understand new research. So thanks again.
All right, thank you.
Thank you, everybody, our viewers watching us from somewhere on this planet. This was a SETI Live by the SETI Institute. You can visit our website at seti.org. We are a non-profit organization dedicated to the search for life, the search and the prevalence of life in our universe. So that's the reason we have this live where we talk about astrobiology, recent discovery in the field of astronomy, astrophysics. So you learn about the wonder of space exploration. If you want to support us, you can simply like this video, click like, share it, comments, ask questions. Matt and I will take the time to look at the comments and maybe take some to answer to some of your questions if we did not address everything. And you can also go to our website, seti.org, and register to get our newsletter, called Journey. Or also, if you're inclined, you can make a small donation. Go to seti.org slash, I think it's donate, but the link may pop up at the bottom of this video. But anyway, it's a button on the right side, click donate, and you can make a small donation to support our research, our outreach, and get more programs like that at your home on a weekly basis. Thank you very much, everybody. Take care, look up, enjoy the dark sky, and look at the moon. It's almost full, so it's the time to do it. Bye bye, Matt.
All right, bye. Thanks.